Hi everyone, in this video I'll be talking about 4.6, limits at infinity and asymptotes. Limits at infinity basically are a way of figuring out what a function is doing towards the end of its life. So if you want to know the end behavior of a function, then evaluating the limit for x or whatever the input variable is approaches infinity will reveal what is happening at the end of the function's life. So let's say we had some function that is describing what's going on with this virus. A lot of us want to know what the end result of this virus will be. How many people lost their lives, how many people were infected with it, and so on. So if you have a function that describes that system, perhaps a question you could ask that function is, okay, what is happening when time approaches infinity for this system? And then that may tell you what's a likely result of this outbreak. So I'll let you read through these definitions yourself. I'm going to try to keep this to be a short video. So let's work on an example. First off, I guess this theorem is useful. So what we're going to be seeing is that we're going to develop a lot of occurrences of these power functions. So if r is greater than 0, in other words, if it's like a half, something like this, then this would be a rational number. R would be a rational number, and if that's the case, then 1 over x to that rational number will be 0. In other words, as this x gets very, very large positively, then this denominator gets very, very large, and 1 over very, very large approaches 0, right? If you're approaching negative infinity, then again, as x takes on more and more negative values, then 1 over very, very negative means 1 over very large in magnitude, which means 1 over very, very large in magnitude also approaches 0. Here's a particular case. So if you have 1 over x to the first power, as x approaches infinity, right, as x is getting very, very large this way, then you can see the output value of the function is approaching 0. As x gets very, very large negatively, then you can see the outputs also approach 0 as x is going that direction. So you would have the limits literally be 0 for this function as x approaches positive and negative infinity. All right, so for example 1, there is a technique that we're going to apply here. So what I'm going to do is actually look at the denominator. I'm going to figure out what the largest degree term is in the denominator. So it looks like I have x cubed, and what I'll do is I'll actually divide every term by x cubed, the largest degree term in the denominator. That way I'm dividing out what's going on at the end, and I'm able to see more up front what this function's kind of destiny is, if you will. So I'm going to divide each term by largest degree term in the denominator. Okay, so what I'll do is I'll go, okay, this is equal to the limit as x approaches infinity, and this is only the case for x approaching plus and minus infinity. You cannot get this same approach to work out if you're approaching 5 or something. So I'll go 1 over x cubed, right? I'm dividing 1 by x cubed, the largest degree term in the denominator, minus x squared over x cubed over x cubed over x cubed minus x over x cubed plus 1 over x cubed. And now I'll simplify this. So limit as x approaches infinity. 1 over x cubed, I'm just going to leave that. There's no simplification that I'm going to do there. Minus, so I have x squared over x cubed, so I'll have 1 over x there. This is all divided by x cubed over x cubed, which is 1. X over x cubed, so negative 1 over x squared. And then 1 over x cubed, I'll just have 1 over x cubed. Now what I'm going to do is kind of quickly use our limit laws, and I'm really going to imagine that I'm taking the limit of this term, this term, this term, this term, and this term. Maybe I'll just write it out here, but I'm not going to write it out that much going forward. So I'll have limit as x approaches infinity of 1 over x cubed minus the limit as x approaches infinity of 1 over x over the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x squared plus the limit as x approaches infinity of 1 over x cubed. So now what I'm going to do is basically apply this theorem several times. Okay, so limit as x approaches infinity, if I imagine that x is getting very, very large positively, like imagine x is a billion, 1 over a billion cubed is approaching 0. So what I'll do is I'll just essentially say this thing goes to 0 for sure, right? As x approaches infinity here, again, imagine x is a trillion or something. 1 over a trillion would be a very, very small number. So as x approaches infinity, as x gets larger and larger and larger, this result approaches 0. So I literally have 0 here also. The limit of a constant is exactly that constant. So I'll just have a 1 there. And then I'll subtract 1 over, or the limit as x approaches infinity of 1 over x squared. So again, as x gets very, very large, 1 over x squared will approach 0. Same type of thinking for this term. So in other words, after the limits have taken place, I have 0 minus 0 over 1 minus 0 plus 0. In other words, 0 over 1, in other words, 0. Okay. So on to page 71. So I'll go ahead and do part 2 here. So here we have our new rational function. Again, what I'm going to do is look at the denominator and pick out the largest degree variable. That's this x cubed. And I'm going to divide each term by x cubed. Okay? So I'll have that this limit equals the limit as x approaches, I'm approaching negative infinity this time, of 4x cubed over x cubed plus 6x squared over x cubed minus 2 over x cubed all over 2x cubed over x cubed minus 4x over x cubed plus 5 over x cubed. Let's simplify this. So we have limit as x approaches negative infinity. Here I'll just have a 4. Here I'll have 6 over x. And here I still have negative 2 over x cubed. Down below I'll have just a 2. right? X cubes cancel. Now I have minus 4 over x squared plus 5 over x cubed. And again, I'm thinking of this limit kind of passing through and applying to each term. So I'll say limit as x approaches negative infinity of 4 plus limit as x approaches negative infinity of 6 over x minus limit as x approaches negative infinity 2 over x cubed all over limit as x approaches negative infinity of 2 minus limit x approaches negative infinity of 4 over x squared. And finally, this is a lot of writing, I realize. Actually, I tend to, right at this step, just start saying, oh, 0, 0, 0, 0, 4 over 2. Here I'm just showing you guys again, I'm writing a lot of work, but maybe all these limits will just be happening in the background as you do these in practice. So x approaches negative infinity, 5 over x cubed. So again, using that theorem on the previous page, limit of a constant is just that constant. Limit of 6 over x, as x gets very, very negative, imagine x is negative 1 trillion. Negative 1 trillion is now approaching 0 as well, just from the negative side, but still, this whole thing vanishes to 0 in the limit. 2 over x cubed, again, as x gets very, very negative, then x cubed will be even more negative. So 2 over very, very large in absolute value means that this term is 0. The limit of a constant is that constant. Here is another 0. Here is another 0. So after the limits play out, we have just 4 plus 0 minus 0 over 2 minus 0 plus 0. In other words, we have 4 over 2, or 2 as the limit. Okay, let's try one more. So on to page 72. So this is not a rational function, right? It's not a polynomial over a polynomial. But still, this process of dividing by the largest degree term in the denominator can be applied. And again, that's only when we're approaching infinities. So what I want to do is think about, okay, what is the largest degree term in the denominator? You might think that it's x to the 4th, but really that x to the 4th is kind of living under a root. I know there's a 1 here, but I'm just ignoring that for now. So when that square root applies to the 4th power, technically you would actually get x squared out of that. Right? The square root of x to the 4th is x squared. So it's not that x to the 4th is our largest degree term in the denominator. In actuality, there's really something like x squared in the denominator. Right? Because we have the square root of x to the 4th, not just x to the 4th. So in actuality, technically, what we have down here is something like an x squared. So that will be the thing that I divide by, not x to the 4th. Okay, so I'll have the limit as x approaches infinity of x squared over x squared over the square root of x squared. If I'm dividing by x squared outside of the root, that'll mean that I would need to divide by x to the 4th inside of the root. Right? So I'll have x to the 4th over x to the 4th. Dividing by x to the 4th inside of the root is like dividing by x squared outside of the root. Plus 1 over x to the fourth. So simplifying, I have limit as x goes to infinity of 1 over the square root of 1 plus 1 over x to the fourth. Again, I'm thinking of this limit kind of coming inside of this function appropriately. So I'd have limit as x approaches infinity of 1 divided by the square root, right? We can pass the limit under that square root. So we can say square root of the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x to the fourth. And this is all happening under that square root. So limit of a constant is just that constant. So I'll have 1 over, again, square root. Limit of a constant is that constant. So I'll have 1. And as x gets very, very large, then 1 over x to the fourth approaches 0. Right? 1 divided by very, very, very large is essentially 0. So in other words, we get 1 over the square root of 1. In other words, 1 over 1, which is 1. All right, I'll do the other problems separately and attach the solutions there. All right, talk to you next time.